So again, apologies for not getting the videos posted sooner, but they are both on YouTube now. Uh, did the one full Riemann sum problem start to finish. And again, you do want to get comfy with the sigma notation because it's going to show up again. And it's the kind of thing that shows up in a lot of surprising places. All right, so now we have the definite integral. All right, so we defined the indefinite integral to be the antiderivative with the plus c. But now we're going to see that the Riemann sum, finding the area under the curve, which felt like very left field. Why are we learning this? Because the definite integral is the area under the curve. So if the limit exists, then the function is said to be integrable on the interval a to b. So why does it represent that? So some of the properties about definite integrals, if I do the integral from a to a, so at a single value, I get 0. I'd get whatever the function value is, but because I'm going from a to a, the width of the rectangle, even split a whole bunch, is still 0. When I'm looking at the bounds of integration, if I flip them, then I can just multiply the integral by a negative sign. And sometimes we can split an integral into two smaller integrals. Um, there's a couple reasons to do that. We usually don't really see that till way later, but a lot of times it has to do with like whether the curve was below or above the x-axis, or the curve decreased and then increased. Like especially if a point is not differentiable, we'll sometimes split an integral to be everything before the weird point, everything after the weird point. And we already know they play nicely with sums and differences and constant multiples. Okay, so here, did people not get the memo about today? People did not get the memo. Okay. All right, so we've got a couple of definitional, like we're being told the integral from 11 to 12 of f of x dx is -3. From 11 all the way to 17, it's -9. And then the integral of g of x from 11 to 17 is -23. Now, if I look at the integral of g of x from 12 to 12, well, that's the same number. So this has no width, so it has no area. All right, when I'm looking at my g of x here, this one is 17 to 11 instead of 11 to 17. So I'm just gonna flip my bounds and put the negative sign. And now I know this integral is -23. So with the negative I put to flip the bounds back to correct, it means this integral we were presented with equals +23. And then over here, the integral from 11 to 12 of 6 times f of x, the 6 can be factored out. And so we're just doing 6 times -3. So it's just using some of the base properties, manipulating, and then using the givens, forcing them to show up. All right, now, same setup we just had, but now we're looking at the integral from 12 to 17. So earlier, my property told me that I can split an integral with a number in the middle. So my integral from 11 to 17 can be split into the integral from 11 to 12. And then we'll pick it up from 12 to 17. So this 12 to 17 is what they're asking for. So I know the thing I want is now going to be the integral from 11 to 17 of f of x. And then we're going to take away the integral from 11 to 12. So this is going to be -9 minus -3, which would then be -6. All right, now we got two different functions in there, but my integral does break across addition and allows constants to be pulled out. So I'm first going to split it across the addition, and now I'll move the constants out. And now these match our givens. 11 to 17 of f. This is 4 times -9 plus 9 times 11 to 17 of g is that ridiculous -23. Ugh. Calculator time. -243. All right. So these are not too bad. We did similar kind of ones with limits and with derivatives. All right. So there's going to be some questions in the homework that are asking you to evaluate a definite integral. They don't want you to actually go through the whole process of finding the antiderivative and plugging the numbers in. Certainly we could do that on this one. It's a linear function, so we know the antiderivative is a quadratic. But like the one after this, we can't integrate this one without doing some weird trig substitution. So we can, though, do this by looking at the picture we're given and then making a determination about like what that shape will be. All right, so 4/9 of x minus 5. So this is a line that starts at -5. If I plug in 2, so this is on the interval from 2 to 6. So I'm wanting to know the area between the x-axis and this curve. Uh, all right, so by the time we get to x equals 2, this will be positive. The slope is positive, so it'll be uphill. All right, and our y-intercept is actually way down here at -5. So like at 2, it's not crossing the axis. So we have this triangle with an added rectangle, or we can just see this as a trapezoid, like if we turn our head to the side. So there's the little base, the big base, the height. Now, a trapezoid can actually be thought of as a wonky rectangle. So if I figure out my midpoint, and assuming I've drawn with short lines, like straight lines rather, then this piece that's outside can be like cut and rotated up to fill in the blank there. So we actually do have a rectangle. The length here, which is the midpoint here, is the average between the two lengths of the bases. And then our height here is the width here. That's what we multiply by. So we average the length of the bases times the height, or we're going to average the two function values times the width of the interval. So our area is 1/2 of f of 2 plus f of 6, and then times the width, which is 6 minus 2. Now, if that curve on top was not a straight line, we'd be dealing with a different shape and we'd actually be doing some full-blown calculus. This is not a nice number, though. It's ugly. So 4 divided by 9 times 6 minus 5 plus open 4 divided by 9 times 2 minus. So that's -6.4 repeating. Then we divide that by 2. And then we multiply that by 4. And this area is -12.8 repeating. So that's -12 and 8/9. So if I do 12 times 9 and then add the 8, this is -116/9. So certainly the -12 and 8/9, is telling you, oh, this is, why are we getting a negative? Because 2 times 4/9 is small. It's less than 1. Okay. The idea still holds true. We're just looking at an area completely below the axis. That's just an odd example. All right, this one actually works out nicer. The formula we're looking at is ugly to look at, but if we graph it, what we actually see is that this is the top half of a circle. So the square root of 36 minus x squared, that can be rearranged to be x squared plus y squared equals 36. So this is a circle of radius 6 centered at the origin. So when we're looking at our first one with the bounds from 0 to 6, that is looking at this area here. So that shape, that is 1/4 of a circle. All right, well, we know our area of a circle, that's pi r squared. And our radius here is 6. So 6 squared is 36, divided by 4 is 9. So our answer for our quarter circle is 9 pi. So if instead I look at from -6 to 6, now I'm including this other quarter circle. So I'm just going to take the result I got and double it. But this will be half the area of a circle. So in Cal 2, you're going to start to look at some weird areas and then you're going to start to do some crazy things with them, like rotate them to make volumes. But the first part is really linking this idea of the integral, the definite integral from A to B is the area under the curve from A to B of whatever the formula inside the integral is. All right, so this one's a little weirder. So absolute value graphs are like typically a decreasing straight line. It hits the point that makes it 0, and then it's an increasing straight line. So if I can figure out where this is 0, and if that occurs on our bounds, then I can a little more creatively figure this out. So before 14, this is going to be a decreasing graph because absolute values make like a sharp cornered V. The 1/7 is going to make it a really wide V. If it was like 7x, it'd be a sharp and narrow V. So when I look at this graph, I see two triangles. So I've got my two different heights, which the height is the function value. So f of 12, and then over here it'll be f of 17. My base, this one is 2, and this one is 3, just looking at the difference between the numbers. So we're looking at the area of two triangles. So 1/2 area of a triangle is 1/2 base times height. So 1/2 2 times f of 12 plus 1/2 of 3 times f of 17. So I just need to crunch up and figure out those ugly numbers, and then we'll have it. So 12/17, 12/7 minus 2 wholes is minus 14/7. So this is -2/7. All right, so and those cancel. Plus this one will have 3/2 times 17/7 minus 14/7 is 3/7. So this is now 9/14. And then this one is -4/14. So we get, this should not be negative. Because the function's last step is do the absolute value. So this is actually going to be +2/7, which is +4/14, which will be 13/14. But this is a classic like split the integral setup. Our first triangle is the integral from 12 to 14. And then our second triangle is the integral from 14 to 17. That's all the notes we had on this. So this was not a particularly long section, but that is also because this particular, like, at the end of the semester in the spring, they were still trying to get all the way to section 5.5. We are not, so it is not quite as hectic for us. But let me see what we got for the homework in there. The definite integral. 5 problems. That's either great or nerve-wracking. All right, so a whole lot of crunching and pay attention to bounds. But it's basically the whole, here's like F and G, what they're equal to, answer some questions. Very similar to the first ones we were doing. All right, this one, area under a line, absolute value. Yeah. Another circle and a circle one. Okay, that's all of them. All right, so everything I just did in the notes like directly matches what's in the homework for this section. So what is the homework that's due today? Ah, why in the hell is that due today? Sorry, a 2-day turnaround is just ridiculous. Oh, and then antiderivatives were due on Monday. My apologies, guys, if those, like, I should have fixed those. It has just been one thing after another all semester. All right. So let me do this. Edit one set for users. Come down here. All right, so I set 4.10 to be due today. All right, that's not too bad. It's 5 days, but it includes a weekend. Um, and then antiderivatives were due on Monday, but we covered them on the Friday. That's stupid. All right, give me a sec to fix these due dates because I like to give you guys at least a week. And if it's not at least a week, it's like, why would someone do that? But go ahead and look up which assignment, like you wanted me to, like which section number it was. All right, so I just moved 410 to be due on Monday, the 2nd. All right. And then let me actually edit 5.1 as well. Um, yeah, let me put that one on the 4th. And then 5.2 and 5.3, I'll put until the 8th. Yeah, oh, sorry. Apparently the 6th. Apparently everything closes on 6th. Sorry. Where's the save button? There's the save button. All right. And then the last one real quick. All right, at least the last one was already set to the 9th, so that's fine. All right, so 5.1, question 3. Okay, so this is like walking you through how to do a Riemann sum. or at least that's the intent. How well it accomplishes that is a completely different question. But let's see if we can't figure out together what the heck it wants. Okay, so we're going to calculate the area between the line 5x and the x-axis over the interval 0 to 2. So first, yes, they give us a 0 to start with. Okay. So we're going to divide the interval 0 to 2 into an arbitrary number of widths. They're going to be equal widths. So if I was going to divide that into 7 widths, I'd take the distance between 0 and 2. So remember, we call these are usually A and B. So delta x, the formula for it is b minus a over n. So if I was splitting it into 7 pieces, I'd have 2 minus 0 divided by 7. So the width of each piece would be 2/7. For this one, though, instead of 7, we're just calling it n because we're eventually going to take the limit as that goes to infinity. So this is just 2 minus 0 over n, which is just 2 over n. So that's what they want for our first delta x. It's however long the full interval is divided by n. All right, let's see what the next piece is. Okay, so this was a right endpoint Riemann sum. So the heights of our rectangles are going to be determined by the right endpoints. So first, I need a formula for those endpoints. So remember, our x sub 0 here starts at 0, and then eventually we'll have one that'll be x sub n minus 1, comma 2. But to go from my start to the end of my first interval, I add the width of that interval. So x1 is our starting interval value plus delta x. X2 is what we had for x1 plus another delta x. So we actually end up with our starting value plus the width times 2. And then x3, like I'm writing it in the generic formula here, but we'll fill in the numbers here in a sec. But what I want you to see here is how do I go from these very particular things to that general case? And what we're looking for is the case, the k we're going to write it in terms of is these numbers here. So my a was a fixed constant, my delta x is a fixed constant, but I see here in x sub 2, there's my 2, there's my 3, and I can backtrack over here and write this as times 1. So our a sub k, x sub k will be our a value plus delta x times k for how many subintervals we've gone. So for the actual answer they want to see here, they actually want it for our particular things. So x1 is going to be our starting value of 0 plus delta x we just figured out is 2 over n. So our first value is just 2 over n. Our next value is the 0 plus 2 over n times 2. So we have 2 over n, and then we have 4 over n. And then when we multiply by 3, we're going to have 6 over n. So down here for my K formula, if I actually substitute in the things I know, 0 plus 2 over n times K, then I'm just going to get 2K over n, or you can leave it as 2 over n times K. Either way works. But there's what they want to see in the list part and then what they want to see in the general terms. We're not actually going to do anything with the list part, but for some people, like going through and figuring out those endpoints helps them see the pattern. All right, now we're going to find f of our K formula. So f of x sub k is f of 2k over n. But now we got to kind of rewind. What the heck was f? Ah, there it is, 5x. So down here, this will be 5 times our input, which is 2k over n. And then this can be cleaned up just to be 10k over n. Now they want us to take the formula we just got times delta x, which is the very first formula we came up with. So here, this is going to be 10k over n times 2 over n. So we have 20k over n squared. All right, now let me get the last part. So now they want us to apply the Riemann sum. So apply the sigma notation. So we're going to do the sum from k equals 1 to our arbitrary n of that formula we just came up with. Now this, they actually want us to work it out. So the sigma notation is incrementing k. So the 20 and the divided by n squared, as far as the sigma is concerned, those are constants that are just going to get added on every time. So it doesn't really care about them. So I can factor those outside. So the sigma is really just saying, all right, we're going to add the first n integers. And this is one of the 4 sigma formulas that we're given. We know the sum of 1 is just n. The sum of k is n times n minus 1 or plus 1. I do this every time. Plus 1 over 2. So if we asked you to do one of these on the final, which I don't think we are, we would give you the sigma formulas. But now that we've done that, we can clean it up some more. So the 2 and the 20, that'll reduce back to a 10. And then this is n squared plus n. You know what? I can cancel this n with one of these. So it's 10 times n plus 1 over n. WebWorks should take this as the result for that part. And now we just need to do the limit of this result. So this is going to be the limit as n goes to infinity of 10 onto n plus 1 over n. All right, so if I plug in infinity, I get infinity over infinity. So I can use L'Hopital. And L'Hopital actually turned out nicely because the derivative of n plus 1 is 1. The derivative of n is 1. So we're just going to get 10 as the result. But we could also distribute and split the fraction. So 10n plus 10 over n and over n. This will go to 0. This, the n's cancel out, and we just get the same 10. So the graph of f of x equals 5x, the area under the curve from 0 to 2 is 10. And this creates, like if we look at the graph, this is a diagonal line through the origin. So when I measure over to 2, well, there's my base. If I figure out the height, f of 2 is 5 times 2, which is 10. So 2 times 10, and then half of that is 10. So this ridiculous 10 checks out. So that was very long, kind of convoluted. But did that help, like, make sense of how we're putting the pieces together? Like, hopefully it makes the x sub k part, like, easier to see. I'm not, like, writing it quite the way most people would think through it, but I'm writing it from the, we're going to have to abstract this to a formula, and that's the part that tends to confuse most people. And this holds true for any right endpoint, which I think that's what all of the homework does. So I don't think they threw in a left or a midpoint in there. And now we have an extra Riemann sum in a video. 2 is better than 1. More is better than less for examples. But what we're also going to see is the integral from 0 to 2 of 5x is the antiderivative evaluated at 2 minus the antiderivative evaluated at 0. Like, we're going to see an even shorter way to answer this question when we do the fundamental theorem of calculus on Monday next week. So you just have one day of these stupid Riemann sums, and then you can ignore it until you get to the end of Cal 2 when you're going to have like a month of sigmas. All right, let me go ahead and stop the recording.